Hello ladies and gentlemen, and welcome to part 3 of this pre-course preparation on quantitative methods. In this part, as you can see from the slide, we're going to discuss the topics of probability and probability distributions. And over the course of the next hour or hour and a half, I'm going to take you through a number of slides, and after that, as with the other topics, there are some exercises that you can go through for which you will have the solutions which will help you understand the topic better. Now, when you get to the end of this topic, there are 3 key questions that you should be able to answer, and answer quite easily, be quite comfortable with the answer to those questions. And those 3 questions are: what is probability? What does it mean? Question 2, why do we use them and when do we apply it? And question 3, how do we calculate them? Now, without wanting to spoil the surprise, in very few words, probability is the likelihood that a certain event will occur. When do we use it? Pretty much any time we need to make a decision. When you're crossing the road, you are calculating probabilities. You may not think about it, but you look, see if the traffic is coming, and your speed may adjust. What are you doing? Calculating the probability that the car or other vehicle will get to you before you get to the other side of the road. So pretty much in any circumstances, in any situations in life, you are doing that. And number 3, how do we calculate it? There are different ways, and we're going to go through them in the next few slides. So as a reminder, and I'll be very quick through these first few slides because you hopefully have seen them in the first 2 topics. The aim of these notes is to either teach you something that you have not yet learned before and raise in you the awareness of the topics and where to go and look for answers and go and look for materials to learn. Or for those of you who have studied but either have studied in a different language or haven't done it for quite a while, just to remind yourselves of these topics. This is the 3rd one, as I've just mentioned. We're going to be discussing probabilities and probability distributions. The other 4 are key mathematical concepts. The second one, data exploration, and then we're going to have 2 more on simulation and optimization, and finally on financial maths. As always, I'm going to be doing this recording, and you've got the notes that go with it. There will be some practice exercises with the solutions. And also at the end of every topic, including this one, there's a list of references, books that you can go and look for these materials that we covered and learn them in more detail, use more exercises to practice more if you so desire. So now let's go to the topic of the session, which is probability and probability distributions. As always, there's no better part to start than with definitions. And the key definition of why we need probabilities and probability distributions, why we need to understand them and why we're going to use them, is very simple. In business, no matter what business it is, we are constantly making decisions. As managers, we are deciding what resources to bring into your business, how to use those resources, when to stop doing things, when to start doing things, etc. Whatever the decision is, it's constant. And those decisions are always about the future. The past is gone. There's nothing we can do about it. We can't change it. What we can do is, if it wasn't good, we're trying to fix it. If it was good, we're trying to replicate it. But irrespective of what it was, we can't change it. What we are changing always is the future. And the future, as it says in the slide, is uncertain. We do not know what's going to happen in the future. And even when we make a decision with a certain objective, we don't know if we're going to be successful or not. And even if we are successful, we don't know how much. So we launch a new product. What can happen? Market may want the product or may not want the product. Want the product, success. Not want the product, failure. But success, maybe we'll sell enough to break even, or we will have such demand for the product that we're going to have to double or treble our production capability to meet that demand. Very different levels of success. So there is uncertainty about the future. There is uncertainty whether we make a decision or not, but there is uncertainty even after we've made a decision and even after we have some idea of how successful our decision was. So we have uncertainty that we have to deal with, and we have to try and manage it and try to minimize it. And we have a number of variables that are random, and by random doesn't mean that anything can happen necessarily, although in some cases anything can happen, but random means they will take different values. In most cases, those different values will be within a certain expected range. In some cases, it will be any value whatsoever. So, for example, there are variables like profit, productivity, etc. It can be very high, it can be very low. So it can take a very large number of outcomes. And what are we trying to do in business? We are trying to understand those random variables, try to protect ourselves against variables that may hurt us, like the success of our competitors, like the suppliers not having enough materials to supply us with the quantity we desire, like a number of our employees not being available to perform their tasks. So any of those, we are trying to minimize the impact of those, putting systems in place, putting decisions in place that if something goes wrong, we have a backup. And there are variables that we are trying to actively manage and improve. Things like profit, productivity, reduction of waste, all of those, we are actively managing them and trying to shape what the future value of those variables are going to be. So we are trying to manage random variables under uncertainty, and for that we're going to make decisions. And those decisions, because their outcome is also uncertain, we have to try and understand as much as possible how likely different outcomes are once we make those decisions. And that's when we calculate probabilities. So as it says in there, it's up to the management of every company to try to predict the values of variables and try to impact variables like profit, productivity, revenues, etc. as much as possible and reduce that uncertainty. How do we do that? Using probabilities. How do we do that? By saying, if I do X, likely outcomes are A, B, C, and probabilities of those happen is going to be X%, Y%, Z%. And then we make the decision on that basis. So We may say if this product is successful, we're going to have very high profits. But if we run some market tests and there's only a 10% probability of that product being successful, probably it's not a good idea. So it's through calculating the likelihood of different outcomes, that is, the probability of that outcome happening, that will then allow us to determine what is our expectation about the value of the variable we are trying to impact and make our decisions. So as it says in the slide, the management of those random variables is achieved partly by determining the probabilities of the different outcomes. And in most cases, obviously, never forget, and this is not in most cases, this is in every case, we are trying to control the future. But we can't control the future. We do not know the future. And every day we see evidence of situations that we try to control, but a different outcome happens. So we can never be convinced that we are right. But what we can do is, as much as possible, use evidence to support our decision. And that's when, in most cases, we're going to use samples. Samples of things that are equal that have happened in the past, or samples of things that are similar that have happened in the past. And we're going to build our knowledge based on that, based on using those random samples. And from those random samples, understanding the behavior and predicting the future behavior. And we do that by, as it says in that last bullet point, by building models, whether they are regression models, whether they are hypothesis testing, whether they are simulation models, whether they are decision trees, whatever type of outcome, whatever type of model, we develop it by using past information and then using that model to predict future outcomes. So how do we actually do it? Well, there's two types of activities that most businesses get involved, well, all businesses get involved in. There are the repetitive activities, where even if they are not exactly the same, they are very similar. So you take a chain of stores like Marks and Spencer's or a supermarket like Tesco. Over the days, the months, the years, they collect data of what products customers demand, how many units they sell of the product, what price they can charge for the product. And so every time a new company or an existing company comes with a new product and tries to convince them to put them on the shelves, whether there is food, whether there is articles of clothing or articles for the house, for the home, whatever it is, they can go back and say, all right, what type of similar products have we dealt with in the past? How successful were they? And make their decisions on that basis. And then you've got the other types of activities or decisions that, due to their characteristics, either because they are very big, for example, building a yacht, a yacht specifically for a customer, a wealthy customer, so a made-to-measure yacht. It's the first one you're going to build like that, whatever they want, however many swimming pools, however many rooms, etc. It's going to be a different. You can do something similar, you've done something similar, but at the end of the day, it's going to be a different project. Or most examples like a big construction, public works, for example, the example there, building a bridge, building a new road, whatever it is, so building a new school, etc. So all of those end up being so unique in most cases, that you don't have anything that was done that you can use to calculate probabilities. And so those are the two key ways and the two key views in which probabilities are calculated. One is called the frequentist view, where, because there's a lot of repetition, we look at the frequency with which, when we do something, when we make a decision, when we take a certain action, what is the probability of a certain outcome. Subjective view is when we just use our own expertise, and what we do is, all right, never done this before, let me try now. So let me try now based on my knowledge to come up with a probability. And so those are the frequentist and the subjective view. So frequentist, we can use samples, we can use experiments, which we'll see in the next few slides. Subjective view, as the name says, it is subjective. It is based on a lot of knowledge, a lot of expertise that you've built over time that allows you to determine the probability of a certain outcome. So for the frequentist view, what we have is a way to determine a probability, and there are two ways to do it. One is we have what's called a priori probability, where we know all the different outcomes, and from that we can determine a probability even without doing anything. So there's an example there. I'm going to give you another one. Take a pack of cards. There are 4 suits of 13 cards each. So what's the probability of taking a spade, which is one of the suits? 13 cards are spades, 52 cards in total, 13 out of 52, or 1 out of 4. So there's a 25% probability of taking a card that is a spade from a pack of cards. And that's straightforward. You know all the possible outcomes in that particular population, and you know what you define as success, which in my case I defined as a spade. Now what that means is, if you then take a card, for the next time you try and take another card, if you don't replace the card you had before, the probability changes, because now you no longer have 52 cards, you only have 51, and you either have 12 spades out of 51, or you still have 13 spades out of 51, so then the probability will change. And to calculate that, as it says in there, number of ways that the event success can occur. I said take a spade from the pack of cards, that's 13. Total number of possible outcomes, 52 cards in the pack of cards, 13 out of 52. The other way to calculate the probability using the frequentist view is when we can conduct an experiment. So even if we don't know what the probability of something is, as with the example of the cards, you can just do something many times. And once you've done that many times, whatever the number of successes you had over that number of times you repeated the experiment becomes your probability. So again, using now the example of the die, if I throw a die 600 times, the likelihood is I'm going to have roughly 100 ones, 100 twos, 100 threes, etc., up to 100 sixes, and that becomes our probability. 100 over 600, 100 over 600, or 1/6. Okay, same with that example. The likelihood if I toss a coin 500 times is that I'll get 250 heads, 250 tails. And so that will become my 50% probability. Now, I've been using some words, so let's make sure that the words I've been using are clear to everyone and we all have exactly the same definition. So an experiment is something that you conduct, that you do something to see what happens. So, silly example, I'm going to jump from here to there to see how far I can jump. So that's an experiment, and then I keep trying, and then I run a little bit more, or whatever it is. So that's an experiment, a physical experiment in that case, but an experiment nonetheless. And so conducting an experiment is just doing something just to see what the outcome is. Within an experiment, you've got the outcome, so which is the result that you get from that experiment. But each time you conduct that experiment, you call that a trial. So I'm sure you've heard the concept of trials in court. That's an experiment, which is there is supposedly a crime that was committed, there is a trial that takes place, judge the different outcomes, guilty, not guilty, and there is an outcome. The accused either is declared innocent or guilty, which is the same. Toss a coin, there is that's a trial, there is an outcome, head or tail, and so then you can do it again. The same way in courts, you keep doing it. You probably have heard of medical trials as well. Same thing. What are we doing? We are experimenting with a drug, see how effective it is in treating a condition, see what the side effects are, and then you use the outcomes of those trials to decide whether to go ahead with producing that medication or not. So this is same in business. You can do the same. Now, in business, obviously, there are some things that you can do, such as you can produce a prototype of a product, see how it works, see what needs to change, then you can produce another prototype, etc. Obviously, you can't keep launching products, but you can do some trials on some part when you're developing products, for example, or when you are deciding on logistics networks. You can decide the routes that a truck takes, so things like that. You can still do trials on that. Three more things that are important when we are dealing with probabilities. On any experiment, there is a sample space, and the sample space is made up of every single possible outcomes. So in the case of throwing a die, sample space is the numbers 1, 2, 3, 4, 5, or 6. In the case of a pack of cards, the sample space is the 52 cards that you have in a deck of cards, and so that's the sample space, all possible outcomes. Within the sample space, a lot of times more than one event can happen, more than one outcome can happen, but some cases that's not the case. So you either weigh 40 kilos or you weigh 50 kilos or 60 or whatever it is. You cannot have two weights for the same person. So although there is a sample space of all the weights that a human being can have, every single weight on every single individual trial is mutually exclusive, because if you have one, you can't have the other. Okay, so that's the definition of a mutually exclusive outcome. Compound events is when success can be achieved by different outcomes. So, for example, when you throw a die, I can define success as throwing a 1, or I can define success as throwing an even number. in which case if I get a 2 it's success, a 4 is success, a 6 is success, and that's a compound event. Now for probabilities, two of the most important characteristics are the addition and multiplication rules on probabilities. So when you have what we've just saw, compound events where more than one number is considered as success, to calculate the probability of success, you add the probabilities of each individual outcome. So in my example, 2, there's a 1/6 probability, 4, there's a 1/6 probability, 6, there's a 1/6 probability. So if success is 2, I've got a probability of success of 1/6. But if it is an even number, then the probability of success will be 1/6 plus 1/6 plus 1/6, as it shows in there. Now, one thing that is important is that sometimes, if we're looking at events and calculating and accept that more than one outcome constitutes success, sometimes there may be an overlap. And so in that case, we have to take the intersection, that overlap, out, otherwise we'd be counting it twice. So for example, let's say I'm looking at a universe of 20 companies and I say calculate the probability of a company selling more than 100 products and having a profit about £1 million, above £1 million. So let's say, for the sake of argument, out of those 20 companies, 5 of them sell more than 100 products and 7 of them have a profit above £1 million. So I could say 5 out of 20 plus 7 out of 20, that will be 12 out of 20. So there's a 60% probability that a company will either sell more than 100 products or make a profit above £1 million. What if 2 of the companies do both? Then what that means is I have 5 that sell more than 100 products, 7 that have got profit above £1 million, but I don't really have 12 that do one or the other, because 2 of them are in both groups. So what I have to do is I have to add the 5 and the 7, but out of those 12, 2 of them are there twice. So I have to take away one of the times when they are there. I don't have to exclude those 2 companies, but because in the 5 the 2 are there and in the 7 the 2 are there, they're there twice. So I need to take 1 away. So I'll do 5 plus 7 minus 2. So a total of 10 companies either sell more than 100 products or make a profit above 1 million, or do both. There's only 10, and therefore the probability in that case was not 60%, but only 50%, 10 out of 20. Okay, so if you look at the notation on the slide, what it says is probability of A or B equal to the probability of A union B. That's the meaning of that sign, union being A or B, is equal to the probability of A, in my example more than 100 products, plus the probability of B. So more than 100 products will be 5 out of 20, which is 25%, plus the probability of B, 7 out of 20, 35%. So 25 plus 35, 60%, minus probability of A and B. the intersection between A and B, which in that case was 2, or 2 out of 20, 10%. So it'd be 25% the probability of A plus 35% the probability of B minus the 10% of the intersection. Okay. Now, multiplication happens, and we use it when one and the other are required for success. So in this example, success will be, if we define it as companies that sell more than 100 products and have got profit above 1 million. In my example, there was only 2. So in that case, what we do is we multiply the probabilities. So that would be 35% times 25%, and there would be the probability of both happening. Okay, so and now in this case, you are requiring both things to happen at the same time. And so in that example that you've got there on the slide, obviously if you're only throwing one die, you do not have a compound situation like you have in here. To use the multiplication rule, you need more than one event, either more than one event, so in this case throwing 2 dice, or requiring more than one outcome. So for example, if I'm looking at a population, success will be people with blue eyes who are more than 1.80 meters tall. So you need the both. So you'd look at the probability of having blue eye, probability of being 1.80 meters tall or more, and it's the product of those two probabilities that will give you the probability that somebody has blue eyes and is 1.80 meters tall or more. So addition, you use when more than one outcome, but you only need one, but more than one constitute success. The multiplication rule, you use it when more than one outcome is required to achieve success. Okay. The next stage, let's call it, in terms of probability, is what's called conditional probability. Now, when you're in business, you're trying as much as possible to control the future, and you improve your control over the future by having more information. And so that allows you to determine that, for example, rather than say the probability that I will make a profit above 1 million is X, you can say the probability that I'll have a profit above 1 million if I manage to sell this many new units is X. If I sell less is Y. And so you can get a better understanding of possible outcomes. So I can say, for example, that on average, let's use a silly example, on average, I am on time 80% of the time. So the probability that I commit to getting to a certain place at a certain time and I deliver is 80%. Okay, so for example, how did I get that? Based on past evidence. For every 100 commitments I had, 80% of them I was on time, 20% of them I was late. Now I can go back and say, in rainy days, I tend to be late more than in sunny days. Or in days when I slept 7 hours, I tend to be on time more than in days when I only slept 6 hours. And so now, rather than say probability that I get on time to a situation is 80%, I can say the probability that I am on time on a sunny day is 96%. Probability that I am on time on a rainy day is 70%. Why is that beneficial? That's beneficial because when I make a decision, what time do I need to leave in order to be on time? I'm going to look at the weather forecast and say, tomorrow is going to be sunny, I need to leave at this time. Tomorrow is going to be raining, I need to leave early. That will allow me to control the variable better so that I'll be on time more often. And in business is exactly the same. So what is the probability of success of a product? 60%. But if I price it in line with my competitor, probability that my product will be successful is 75. Or if I do some advertising prior to launch, my probability of success is 80%. So I build a relationship between variables that I can either decide myself, what price I charge, what time I leave home, do I advertise or not, or that I can at least know the outcome of before I have to make a decision. So look at the weather forecast, see if there are roadworks in the route I normally take to get from A to B. So by doing that, by getting more information, I can get a better calculation of probability. All of this long explanation is called a conditional probability, where I gain information about a certain event, and that information will affect the outcome of that event. So the example is there. Another one, probability of drawing a spade is something that I've used earlier, and I said it was 13/52 or 1/4. But if I tell you that I drew a card that is black, then there's 2 suits that are black, 2 that are red. By now, if I tell you that the card that I took was red, even though I didn't tell if it is a spade or not, now there's only 26 cards that are black, and therefore the probability is now half rather than a quarter. Okay, so that is something that, again, businesses are trying to do all the time before they have to make a final decision, to get as much information as possible of variables that affect the outcome of the event, so that they can make a more accurate decision that is more likely to be successful. Now, the ultimate formulation for conditional probability is called Bayes' theorem. And it was invented by a mathematician called Bayes, and it is used to calculate conditional probabilities. Now, there's 2 ways that we can use Bayes' theorem. There is one easier way, the one that we've got here, but then we've got a more complex way, which is the ultimate formulation. And we need to use that one when we don't know a certain probability. So here, for example, we know the probability of a card being black. And so when we calculate the probability of, for example, a spade, given that the card is black, we know that probability of B in this case, which is a black card, and that is half. We also know the probability of A and B, which in this case is spade and black, which is a quarter. A quarter of the cards are both spades and black. So to calculate the conditional probability of what is the probability of taking a spade given my card is black is just 1/4 over half, which is half, as we saw in the previous slide. So that is Bayes' theorem, probability of A and B given probability of B. But in this case we know the probability of B, and so that makes our life easy, but that's not the case in most circumstances. And because of that we have this beautiful formulation here, which is always a struggle to understand, and do make sure you go through one of the references if it's not clear. And what we are doing here is exactly the same we did in the previous slide, but when we don't know the probability of the earlier event. So let's have a look at an example here. We've got three friends. They're going to a restaurant, and the restaurant has only got 3 dishes: a meat dish, a fish dish, and a vegetarian. The 3 friends, let's call them F1, F2, and F3. One of them prefers meat, the other one prefers fish, the other one prefers vegetarian dishes. But they're not exclusive. Sometimes they do eat other dishes. Their preference just simply means that, take friend 1 for example, you would say that the probability that he will pick or she will pick a meat dish will be, say, 70%. Probability that they will pick a fish dish is 20%. Probability that they will pick a vegetarian dish may be 10%. The friend that prefers fish may have a probability of choosing the fish dish of 65%, 25% of, or 20% of choosing the meat, and 15% of choosing the vegetarian, and so on. So then the question that you might have, and this is an example, is calculate the probability that one of the friends ate the meat dish. But it will be different for the different friends. So let's say we know, for example, that friend 1, and we're going to try and calculate for friend 1 what is the probability that they have a the meat dish. So in that case, what are we calculating? We are calculating, again, probability of, as we saw in the previous slide, A and B, which is M and friend 1, given the probability of B. So that's what we're going to calculate here, is the probability of somebody eating a meat dish altogether will be what's in the denominator, probability of friend 1 given meat times probability of meat, plus probability of friend 2 given meat times probability of meat, and the same for friend 3. And then to calculate the probability that we had a meat dish given that it was friend 1, we look at the situation where we got friend 1 and meat dish. So what we got in the top is friend 1 and meat dish. At the bottom in the denominator, probability of meat dish. And that's what Bayes' theorem is all about. Again, it's a hard one to explain, a hard one to get your head around if this is your first time. Make sure you go through the exercises. There's some exercises on Bayes' theorem in the exercise for this topic. Make sure you go through the references and make it clearer. Okay. Another important concept of probability is that when you run an experiment many times, when you have many trials, there are different ways in which you can get to the same outcome. So for example, if I have 2 dice and I want a 6, I can get a 6 on the first one, or I can get a 6 on the second one. Does it make a difference to me? If it doesn't, then both of them are successes. And so in that case, there may be many ways to build the same success. So as it says in there, success may be achieved in different ways, and it may be important not just the ways in which you do it, but the order in which you do it, or it may not be important. In that case, we have permutations and combinations. So say, for example, 20 people enter a draw with 3 equal prices. Your probability of winning a prize will be 3/20, because there's 20 prizes altogether and 3 people are going to get prizes. It doesn't matter if you get the first one, the second one, or the third one, because they are the same. And so in that case, there are 3 ways in which you can get a prize. But if the prices are different, then the probabilities are going to be different. Because for the first one, there's only a 1 in 20 probability of winning the first prize. Once the first prize is gone, there's a 1 in 19 probability of you getting the second prize, because the person who won the first prize is now out of the draw. So there's only 19 people left. And once those first 2 prizes are gone, then there's only 1 left. And there's only 18 people left. So now probability of getting a third prize is 1/18. So in the previous slide, the order didn't matter. So you had a 3 out of 20 probability of winning a prize. Now you've got different probabilities of winning first prize, second prize, third prize. So now in this case, it does matter. So when order matters, what we have is permutations. When order doesn't matter, what we now have is combinations. And as you can see in there, if you take, for example, 10 balls in one bag, 4 of which are green, the number of ways in which I can get 4 green balls within 10 balls, if the order doesn't matter, so if I just want 4, I can only have 210 ways. But if the order matters, you can see what happens. The order increases significantly. Because then what I have is, let's say the first 4 balls are green. In terms of combinations, there's only 1, which is green, 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 green. But if the order matters, then if I have green ball 1, green ball 2, green ball 3, green ball 4 is different from green ball 2, green ball 1, green ball 3, green ball 4. And it's different from green ball 2, green ball 3, green ball 1, green ball 4. And I can keep going, and there's many different ways in which I can do that. Okay, so the way to calculate any of these in ways in which I can have possible success from a certain number of outcomes is, as it says in there, using combinations and permutations. For that, we need to know three things. We need to know before the matters. We need to know the number of successes, and we need to know the number of attempts. So in this example, number of attempts is 10, total number of balls. Number of successes is green balls, which is 4. And then we need to know the concept of factorial. And factorial is the product of every number from whatever we start until 1. So factorial of 3 is 3 times 2 times 1. Factorial of 5 is 5 times 4 times 3 times 2 times 1. Why do we use factorials here? Because let's say I want 1 ball out of 5. There are 5 different ways in which I can do it. I put it in number 1, in number 2, in number 3, number 4, and number 5. And in order to determine that, the way to do it is to use factorials for the calculation. So in the case the order doesn't matter, I do number of attempts factorial divided by number of successes factorial times the difference between attempts and successes factorial. If I look at permutations, because order no longer matters, the denominator of that calculation I no longer multiply by the factorial of the number of successes, and that means that the numerator is unchanged, but the denominator becomes a much smaller number, and that's why I have a bigger number of permutations. Okay, now let's get into the second part of the topics of this session, which is probability distributions. Now, probability distributions are not different from probabilities. Probability distributions are simply calculation of probabilities of different outcomes of variables that behave in a certain way. Now, why do we use them, and why can we use them? We use them to make our life easier. And we can use them because most variables in life behave in certain ways. So, for example, imagine a game that you enter where you either win or you lose. So once you know the probability of winning, you know what is the probability of winning 3 times when you play 10 times. You can know what's the probability of winning 4 times when you play 20 times, and so on. And you can calculate that. But because there always is going to behave the same way, you don't need to keep calculating. You can use a distribution that behaves in that way. We know that most variables in life, you see most of the observations around a central value, and the extremes are less likely. So take people's heights. Most people's heights vary around a mean height that the majority of the population has. Then you'll have a small number of people who are much shorter and a small number of people that are much taller, but there's a lot less. So in business, it's the same situation. Most variables behave in well-known ways. If that's the case, then we can use these probability distributions, and we don't need to keep recalculating probabilities all the time. So that's what it says in there. A significant number of business variables behave in similar manner. Instead of calculating the probability for each variable, we can use these well-known distributions. Key distinction on distributions. Some variables are continuous, either theoretically between minus and plus infinity or within a certain range. Some variables are discrete, so they can only take certain values. For example, number of phone calls, you can't have 4.5 phone calls. Number of customers, again, you can't have 4.5 customers. So they only take discrete numbers, normally whole numbers. Now, there are a lot of different distributions, and if you use some softwares, for example, for simulation, there's all sorts of different distributions that you can use. But there are 3 distributions that are the most common. 2 of them are discrete. One is the binomial, where there's only 2 possible outcomes, success or failure. Yes or no, exists or doesn't exist. So if I look at the variable, does somebody have blue eyes? They either have blue eyes or they don't. So that would be the case. Or do I win a game? I either win or I don't. Did I win the lottery? I either won the lottery or I didn't. So that sort of situation. The other discrete distribution that is very widely used is the Poisson, where you have a number of discrete outcomes, but more than 2. So phone calls, for example, you either get 0 or 1 or 2 or 3 within a certain time period. And then you've got the distribution that is the most common with continuous variables, which is the normal distribution. So binomial distribution, what do we need to know? We need to know number of trials. We need to know probability of success. And we can then calculate the probability of a certain number of successes within a certain number of trials. So example here, calculate the probability that 2 customers will buy something out of the 15 that enter the store. Historically, we know that on average 3 out of every 20 make a purchase. So the first thing to see is look at the formula of the binomial distribution, and that is always the same formula. To calculate the probability of x being equal to r, where r is the number of successes, we do the combinations of n into r times the probability of success to the power of the number of successes we are trying to calculate the probability of, multiplied by 1 minus the probability of success to the power of number of trials minus number of successes. So in this case, we have n, which is 15, number of trials, r, which is 2, probability that we are trying to calculate, probability of that number of successes, in this case 2, and we need to know the probability of success. That we're going to use either using the frequentist or the subjective view. In our case, this is likely to be a situation where we can use the frequentist because we could have been collecting data for a long time about the number of customers that come into the store and the number of purchases that they make. So we've got that here, 3 out of 20 or 15%. So to calculate the probability of x, number of successes equal to 2, we calculate 15 factorial over 2 factorial minus, times 15 minus 2 factorial, multiplied by the probability of success, 15% to the power of 2, number of successes, multiplied by 1 minus 0.15, which is the probability of failure, to the power of the number of failures. Now, notice we use the powers because it makes it simpler. Obviously, we could do the calculation as number of successes 2, probability 0.15 times 0.15. Number of failures 13. Probability of failure 85%. So we would do 0.15 times 0.15 times 0.85 times 0.85 times 0.85 13 times. So we use the powers. The combinations are there because the two successes don't have to be the first two customers that come in. It can be the first two, or the first and the third, or the first and the fourth, etc. In this case, the order doesn't matter because it's not customer A and customer B different from customer B and customer A. It's any two customers in any order. So order doesn't matter. So we simply do that. Now a little trick. I know we have calculators and computers all the time these days, but a little trick on mental maths. When you look at factorial, because factorial is the product of every number from the number until 1, when you have 15 factorial, it's 15 times 14 times 13 times 12, etc. When you have 15 minus 2, it's 13 factorial. So you can do 15 times 14 times 13 factorial, cross out with 13 factorial in the denominator, and so you're left with 15 times 14 over 2, or 15 times 7 effectively. So you've got 105 possible combinations of two customers buying something out of the 15 that come into the store. Okay. Now, one additional piece of calculation here, just for information as well. What if I wanted not the probability of 2, but the probability of no more than 2 customers buying anything? Then success would be 0 or 1 or 2. In this case of a distribution like this, because it is discrete, you have to calculate each one individually. So you do exactly the same calculation, but you would replace 2 factorial with 0 factorial and 15 minus 0, so there's only 1. And then you do 0.15 to the power of 0 times 1 minus 0.15 to the power of 15. Then you do the same, replacing the 2 with 1, so 15 factorial over 1 factorial times 15 minus 1 factorial times 0.15 to the power of 1 times 1 minus 0.15 to the power of 15 minus 1. And then you've got the probability of 2 here. And to calculate the probability of it no more than 2, you'd add the probability of 0, probability of 1, and probability of 2. Okay. The next distribution that is very commonly used is the Poisson, which, as I mentioned earlier, is used when there's more than 2 possible outcomes, but only discrete possible outcomes. So in that case, we use the Poisson distribution, and all we need, in this case, we need even less than in the binomial distribution, where we need probability of success, number of trials to calculate the probability of a certain number of successes. Here, all we need is the mean of the distribution. Now, obviously, for the mean, we need past information that allows us to calculate that mean, or we need expertise to estimate that mean based on similar occurrences, similar variables that we are aware of. So in this case, as I said, all we need is the mean of the distribution, which is represented by mu, and from there we can calculate the number of successes. And for that, the probability of x, where x is the number of successes, is simply going to be equal to e, where e is the exponential, the number e, which you can look it up on the calculator, and it is a constant, it's not a variable, so it's simply e to the power of minus mu times mu to the power of x over x factorial. So again, there's an example here we've got an ambulance dispatch center that on average receives 20 calls per hour. And we are trying to calculate the probability of 6 calls being received in a 15-minute interval. There's an example that I've put in here to make sure I highlight the fact that you need to always use the time period of the question that you're asked, of what you're trying to find. So notice the average is given per hour, but the question is about a 15-minute interval, a quarter of an hour. You cannot take those 6 calls and make them 24 by multiplying by 4, because there's 4 quarters in an hour. You can't do that. You have to do it the other way around. You have to look at what is the average or mean of the distribution for the 15-minute period, and then calculate the probability of 6. Why? Because getting 6 calls in a 15-minute interval is not the same as getting 6 calls on each of 4 consecutive 15-minute intervals. If you make it 24 calls in an hour and you assess the probability of that, you're making that assumption, but also you're saying you may get 20 calls in a 15-minute interval and then 0, 0, 0, and 4. And you're not in that case calculating the probability of getting 6, because you got 20, 0, 0, and 4. It's not 6. So always you need to change the mean in line with what you're trying to analyze, not in line with the information that you're given for the time period that you're given. So in this example, the first thing is to calculate the mean number of calls received every 15-minute interval, which in this case is 5. So take the 20 calls an hour, divide by 4, and you're calculating the probability of success of 6 calls in that 15-minute interval. So probability of x equal to 6 is going to be e to the power of minus 5 multiplied by 5 to the power of 6 over 6 factorial. And so if you calculate that, it will give you 14.62%. Okay. The final distribution is called the normal distribution. That is by far the most widely used distribution in business. Why? Because most variables in business, whether they are productivity, whether they are profit, whether they are a number of employees, whatever it is, they follow a normal distribution. That is a distribution where looks bell-shaped, symmetric, and single modal, meaning there's only one mode, which in this case is the same as the mean and the median as well. Now, for this distribution, we need to know two statistics or 2 coefficients: the mean and the variance or standard deviation. Now, the mean, supposedly, theoretically, we would need to know the true mean and the true variance or standard deviation of the population, but in most cases we don't. So what we do is we use a sample, and then we use the mean represented by x bar and the standard deviation represented by x for the sample rather than the population. Then, because it's a continuous distribution, we can't calculate the probability of an exact value. What we do calculate is the probability that I will be within a certain range of values. And that's what you've got in there. You calculate the probability of a range in values. Normally, a probability of more than a certain value or the probability of less than a certain value. Now, in order to do that, we could calculate manually, but there is a quite complex formula. But because normal distributions all behave in the same overall shape, what we can do is standardize our normal distribution by doing what's in there, calculating what's called the z-score, which is the value we are looking for, minus the mean of the distribution divided by the standard deviation of the distribution. And then from there, we can go to what's called the normal distribution table and get the probability from there, which are on slides 28 and 29, which we'll see in a moment. So let's have an example. Calculate the probability of a person being shorter than 1 meter 80 if population average height is 174 and the variance is 92.16. First of all, don't forget there's a difference between the variance and the standard deviation. Standard deviation is the square root of the variance, and in the z calculation, the one we need is the standard deviation. So in this case, we're going to calculate the z-score for this. So we want less than 180. Now, 180 is 6 centimeters away from the mean of 174. But if the variance is large or small, that difference can become something very small if it's a very large variance in values, or if most values are very close to each other and therefore the variance is small, that 6 centimeters may be actually very wide. So we can't just say, oh, 180 is close to 174 or 200 is far from 174 and therefore the probability is low or high. We can't just do that. We need to calculate the z-score. And so in this case, what we do, we transform, or what's called standardize, our distribution of 174 and variance of 92.16 by calculating the z, which is 180 minus 174 over square root of 92.16. That gives us a z value of 0.625. So what do we get from that value? We get from that value that 180 is 0.625 standard deviations away from the mean. I repeat, that number of 0.625 that you see tells us that 180, which is the number we are trying to calculate the probability for, is 0.625 standard deviations away from the mean. So if you look at the calculation, 180 minus 174 is 6. You divide that by the standard deviation. So 6 out of the standard deviation gives you the number of standard deviations. So if the numerator was exactly the same as the denominator, that would give us a z of 1, which would tell us that the value we were looking at, in this case 180, would be 1 standard deviation away from the mean. In this case, because this standard deviation is bigger than the difference, it's only 0.625 standard deviations away from the mean. That number of 0.625, we can then go to the table and look at the table. But before we even go there, and we'll discuss them in a minute, just be aware always of this following. When you have the mean in a normal distribution, half of the population is below the mean, half is above the mean, and that's always the case. In this case, we've got a mean of 174. We're looking for a number that is 180. It's above the mean. So if we are calculating the probability of being below 180, that means I've got at least 50% plus a little bit more, which in this case is 73.4%. But make sure you remember that number of 0.625, and we will look at the table in a moment. But before we do that, let's just have a quick side discussion where we can use tables, but we can always use Excel to calculate probabilities as well. There are formulas, binom dist, that calculates probabilities, binom inv, that calculates the number of successes. So binom dist, if we put the number of successes we want, the number of trials, the probability, and an indication of its cumulative or not, using binom dist, that gives us the probability. So if you look at the example of 3 or 4 slides ago, we had we had 15 trials, which were the 15 customers coming into the store. Probability of success was 15%, and we calculated the probability of 2 customers buying something. And in this case, we put the number 0 because it wasn't cumulative. We were just calculating the probability of 2 customers buying something. If we wanted the example I gave at the end of no more than 2, then we would have put cumulative there, and we would have calculated probability of 0, 1, and 2. If we calculate the opposite, binom inv, if we calculate the number of trials, the probability and the alpha, that gives us the number of successes, which is 2. Same thing for the Poisson dist. Again, the calculation we did in the example, x being the number of successes, 6, mean was 5, call-outs in a 15-minute period on average, and again, it wasn't cumulative. Same for the normal distribution, again using normal dist and normal inv. Normal dist, for the example we just gave, x being 1 meter 80, the mean was 174, standard deviation was the square root of 92.16, and in this case we want cumulative because we want anybody who is under 1 meter 80, and so that will give us the answer. Norm inv is the opposite. In this case we can use the information we have. The probability, in this case the probability indicates the proportion of the population that is below a certain number. So because we know in this case we could look, if we look to calculate what is the height below which we have 73.4% of the population, the mean was 174 and the standard deviation was 92.16, we get to 180 centimeters. To finalize, let's have a look at the standard normal distribution, and remember the number from the example, which was 0.625. That is the value of the z-score, and the z-score are the numbers in the first column and in the first row of this table, and is only got 2 decimal places, so you need to turn that 0.625 to a 0.63. And so if you look in the first column, you look for 0.6, and in the second column, in the first row, sorry, you look at 0.03. 0.6 plus 0.03 gives you 0.63. And so you walk across and you walk down and you see the number there is 0.2643 in the intersection. 0.2643 is the percentage or proportion of the distribution that is in the shaded area at the top. And so what is below will be 1, which is the whole distribution, minus that value of 0.2643. So there would be 0.7357. Slightly different from the one we have in there, because when you use Excel for the calculation, you can use all decimal places, whereas here you're only using 2. So it's going to be somewhere between 0.62 and 0.63. But so that table gives you the area to the right. In our case, we're looking at the area to the left. So that is how you interpret. The other way is to look at, if you recall when we look at norm inv, to look at the probability. Let's say, for example, I want to calculate the value of z that cuts off the top 10% of the distribution. Then instead of looking at the z, I look at the numbers in the middle. And if I want to cut off the top 10%, I look for 0.1. And the closest number to 0.1 there is 0.1003. So when you find that number, you go across and you go up, and you will find the values 1.2 and 0.08. So that tells you that a z-score of 1.28 cuts off the top 10% of the distribution. Okay, so with that, I pretty much concluded what I had to do here, and I hope you learned something. But two final things before you go. Number one, this is a very similar table to the one that we just went through, but slightly different in that it recognizes the sample size that we have when we do analysis. So previous one was called the normal distribution table. This is called the t-distribution table. If you look at the shape at the top, is very similar, but the t-distribution table, rather than have a single probability for every value of z, instead of having a z, it uses a t value, and each column represents the probability, or in this case the t value, for the same probability. For example, the most commonly used column is the one that has got 0.025 at the top, which means 2.5% of the distribution on each tail being cut off, and the t value, which is the equivalent of the z-score, can take all of those values from 120706, 430C, etc., all the way down to 1.96, depending on the sample size that you use for the calculations. If you look at the first column, it has something called V. V is called the number of degrees of freedom, which is calculated as sample size minus 1. And the bigger the sample, the closer the t value becomes to the z-score. So if you go to the normal distribution table, you'll be able to see a value of 1.96, cutting off. If you look at the z-score of 1.9 and 0.06, you will find that value of 1.96. I'm not going to go into more detail here, as this is just an introduction. Just be aware that the same calculations we can do using the normal distribution. In a lot of instances, we will use the t-distribution. For example, if you do regression analysis on Excel, that's what Excel uses. And it just reflects the fact that sometimes the data we have, because it's in small quantity, brings more uncertainty to our calculations. And so finally, you've got, as usual, the slide with the references. All of these books should be easy to access. They're all relatively beginners books, but they are books, especially the last one, which have lots of exercises. So if you want to practice and if you want to have a look at different ways of looking at the calculating probabilities and using probability distributions, that would be good. The top two, they're more straightforward, and I believe both of them have got solutions in, which the last one doesn't have. So from that perspective, it will be even better. And with that, thank you for your attention, and see you in the next topic.